So what I want to do is to set up a very simple model that first we can verify the theoretical result of for a static load and compare it with the simulation result. Again, we are following static and linear case in simulation as well. And then we want to see what is the actual easiest part for simulation, because there is a problem with simulating screws, and that's detail. If you want to go to detail of a screw, like simulating threads, that requires a lot of computation power, so we need to know if it's actually necessary to do that. Even without the threads, let's say you have an assembly with like 50, 100 screws, and the thing is that the screws are usually have a much smaller size compared to the model, and that causes a huge difference in mesh size. So you're gonna have a lot of fine meshes for the screws, and that makes your mesh very big and very time consuming to solve. So we want to see if there is a more simple way to actually do that.
Is it around the middle?
Is it one? Let's go with a shorter one. I just need this for applying the load and nothing else. For now, I'm just trying to model the plates, then I model the, could you please trim here? Then I model the screw, which we're gonna go with the simplest way, which is just a cylinder. But for now, let's first model the plate. Where is these two lines? Yeah, seems okay. The size is separate. I'm gonna and I'm just gonna extrude this. It's a plate with two edges for applying the load. Let's go with maybe 50 on this side as well, or maybe 100, just to have a bigger load distribution. Then I put a hole in the center and copy it, and then put a screw in the center. Let's go with M10 in the center. So it's simple enough that we can confirm it with the theory. But the speed you're modeling depends on the setting of your NX as well. So I'm just trying to put it in the center. Yep.
Why has NX driving become so bad? It used to be good, but now it sucks.
That's it. This is the model.
I always use the driver.
So on the so I'm gonna just copy this, but before that I need a new parent assembly to put this under it. You just go to the assemblies and click on new parent assembly. It puts an assembly on the top of it, and then you can save. It will ask for saving that assembly part. Then it looks like this on the assembly navigator on the left, right? Now I can copy another part, but just Control C, Control V on the top, or just right click and copy, and then right click on the assembly and paste, right? Then I'm gonna unpack it because I want to move one of them. So at the end it's gonna look like this, right? And let's move the other one to the other side. So now I have two parts I want to connect with the bolt in the center, and I use a constraint to just put them in the right position for now. like this, making sure that the holes align, otherwise you're going to get some weird errors. The third part is going to be the screw. So I'm going with new component, makes a new component here, double click on it, and I will start modeling the screw. The hole is 10 millimeters, so I go with M10. Select any plane you want, and just a cylinder, 10 millimeter diameter. And the length I also go with 10. Then I mirror because it looks the same. there should be a knot on the other side to hold it, but I'm just gonna consider a bolt and knot as one uniform geometry because we don't want to simulate or model threads. They don't give us more information for the modeling. We are looking for a static load, which is the stress in the center of the shank of the bolt. We are not looking into thread failure now. So the screw head, I'm going with a hexagon, but we can do any kind of head. For 10, it's 17, but as a diameter. Metric. It could be something else with another system, and it's usually I think 7. So this is the head side, and for the knot side I can just mirror this. Where is the mirror feature? And I want all the features on this plane. Please. Okay, let's see the result. Yeah, it looks fine. So this represents a bolt and nut that is going to hold these two plates together. You just need to make sure you unite them, otherwise I get two separate mesh bodies. I have to connect them together. Now it's just one body part. I'm gonna save it, and then I'm gonna place it. I go back to assembly, top assembly. I can move this around. The best way is to use a constraint. Concentric constraint. This circle should go here. Yeah.
Which diameter did you use it in?
10. 10, yeah. So this is the model we're gonna simulate. So now the model is there, we can go application, pre-post. And I want to have all the parts. We're going with a structural, and as I said, this is going to be a linear simulation, a static load. So here, linear static 101. And create a solution. I probably need to come back here later and request some new outputs, but for now it's okay. So the best way to run a linear static simulation is to always have some constraint. If you want to have some constraint and some load, how should I do that? First let's start with meshing. I want to mesh all the parts. It says 8, let's go with 5. I also want to keep it fast. 10 is too much, we could go with 4, but the model is simple. I say I can actually go with 10 without it taking a long time to simulate. So I have the mesh ready, and let's define the material here before I forget. So I want to, let's go with a steel. And now we can activate simulation to apply constraints and loads.
Sorry.
Yep.
If, when you click on solid, sometimes it will speak like override, it's kind of low.
If you mean locked,
Yeah.
you.
Then I simply click override and I choose the material.
Oh yeah, that's possible when you model your part in the modeling app.
No, in the.
No, I know. Listen, when you model in modeling app, you probably applied some material to it, or NX by default is using a default material in modeling.
Okay.
Then you bring your model to pre-post. It gives you this option as well here. If I go back to inherit the material here. Here, you have this option of inherited.
Okay.
If-
So inherited like the assigned.
Get it from the modeling.
Oh.
Yeah. But if you don't, then it says, okay, you already assigned the material, you want to override it. That's why it's asking. So let's activate simulation again. Here I can apply constraint and loads. So I want to fix some part. So I fix this side. Now if I fix this side, how much is the load on the other side? Anyone? 1,000.
The 1,000 work on both or 1,000 on each?
Let's go back. Good question. When you define the load here, it gives you options. Did you want it total per object? Then it will put 2,000 because I'm selecting two objects.
Yeah.
Or geometric distribution means that whatever you selected, I'm going to distribute 1,000 all over it. This is what I want. If I use total per object, it puts 1,000 in the top and 1,000 in the bottom. So go with the geometric distribution. And contact. So for the contact, I'll go to simulation type. I really don't need the contact. I need gluing. What is the difference? For the contact, you define friction. So it is allowed to move, right? Generally, when you fasten a bolt, it's not going to glue there together, but also you don't expect it to move around. So the gluing will do the job without going to the contact loop. It's more simple to use glue. Glue means exactly like contact, but without movement. So it basically, as the name says, it glues it together. I only want to, if you select all of it, let's see what happens. If you let the software auto-detect all the contact, it comes back with 5 pairs. And I can see the pairs if I just go here. So this is 1 pair. So it detects like the shank contact inside the hole as well. I don't want that. I don't want to connect it like that. So we better go. I think it's easier to hide the one part and see the contact from inside. Yeah, like this. So I don't want this contact. Which one is it? From the shank. This one, I can just delete it. And also that one. I think all of the contacts are wrong, and this is the contact between two faces. So we have to define the faces manually. So let's select manually. I go back to contact gluing again, selecting pairs. Make sure here you select pair face, so it's not automatically looping around the body looking for all the faces that are in contact. I want to actually dictate the faces that I want to glue together. And let's hide this. I want to glue this one. I have to bring back the polygons. Yeah, this face is going to connect to this face, and the other one is this one being connected to, yeah, this face. And this should be okay. No, I have to do it separately, or I have more. Yeah, I can just remove the ones that I don't need. This one is correct, this is not. Just delete it. This should be deleted. This one is correct, and this should be deleted. Okay, so it should look like this at the end. So washer face contact to the plate on both sides. Let me bring back the, yeah. Okay, let me save here. So I got the contact, gluing.
Why do you want to do the
It is not actually in contact. It is if you have threads, but as I said here, we don't want to focus on thread engagement or thread failure. That's the next lecture we're going to do. We just want to rely, and that's not always the case. Usually you can have a full shank without thread. So the thread just stands out on the knot side here. That's this part is threaded. The rest is a shank.
So we're doing gluing because we want to see where it's fractures or what?
Yeah, we want to measure a stress inside the bolt. Okay. If I run the simulation without contact, what happens is that this part just goes through these. So it doesn't work. I can define a contact, not glue, but a contact. But contact loop is complicated. It considers friction as well. I don't want to consider. I just want it to be completely like welded. All right. So it gives a faster simulation if you use gluing instead of actual contact. If you are sure there is no relative motion.
What is the benefit of doing this in comparison to an analytical calculation?
You're gonna see here. You're gonna get the same result. But if you're looking for a stress concentration, or this type of simulation in general that has no benefit. This is the wrong way of running a simulation on a bolt, as I said, because I'm wasting a lot of computation power to mesh very small bolts, which I'll only care about the axial stress. So simple cylinder, which has the same cross section all over it. I have a section meeting. Why now? Okay, forget about it. So I'm gonna do the simple method of doing that after this. But let's see the result here first. Then I show you how you actually need to simulate a bolt. But I think this is solvable now. Let's see. Yeah.
Why are you not just using symmetry in this problem?
Yeah, you can. Yeah, actually you should. I'm trying to keep everything else simple. It's easier to, because my focus is on simulating bolts.
So there's absolutely no need to even have the plates.
Yeah, of course. Yeah. Unless you actually want to read the stress on the parts as well, so you solve everything at the same time, right?
Okay. But don't you also have like bolts that are already preloaded?
Yeah, that's another thing that is not possible with this kind of simulation. But I'm going to show you the right way of doing it, which allows you to add preload as well.
Yeah. But that's a bolt inside of NX, right? That's an NX.
You're gonna, if you wait like 5 minutes, I'm gonna do it. Okay, anyone calculated this?
Yes, it's 12.73. I have it.
12.7.
Yeah, I guess it's in every tier.
Like here, I switched the way those.
You have a different answer? No? Okay.
I haven't checked it.
Okay.
If you have, I will be very impressed.
What is the difference between elemental and elemental node?
It averages on the node and element.
No results.
What?
Sorry.
Calm down. It's NX.
Yeah, bro, like.
It's just it always gives you error. Of course it fails. Elemental averages over elements only, while element nodal considers the node and also gives you the option to select the node when you go identify result. You see, I can actually select the element, but I can also select the nodes as well to read the stress. So I have the simulation looks like this, and to just focus on the bolt, you can go here to post view and hide the meshes that you don't want to. So you see the stress on the maximum. If I want to check it, is around 40, which we already know is because of stress concentration and singularities on sharp corners. What I care and what I want to compare with the theory is the average of a stress in the shank. And I can just go with identify result. I want to pick a box selection of all the elements, maybe around here, and average that. That's same result, of course. And simulation sigma is 12.72. What was? Forget about it.
12.73.
I had the same problem.
Okay.
There was
We failed.
a problem with the
72. This is good enough, which shows if your case is a static case in theory, it actually matches very good with simulation. If you are looking for a static linear case and the stress distribution is good enough that you don't have a stress concentration, so you can easily compare it to the theory. But there's a lot of elements just for this one screw. And imagine there is a sealing problem. You have 50 screws all over the part, and then you mesh it, solve it. You're gonna have headache averaging them and finding the cross-sectional stress and all that. So NX has actually a bolt simulation thing, and you thought NX sucks, but not that much. There are useful things you can do with NX. If you go here and more under connections, you actually we tried mesh mating, we tried 1D connection. Now you get a bolt connection, which is just 1D connection with extra steps. So it will do a nice 1D connection. It will represent a bolt with a 1D connection the way I'm going to show it. But before that, I have to get rid of that actual bolt there and replace it with a simplified version that NX is offering. To do that, I probably need to redefine this. Let me see, how can I edit the FEM file? Let's go here, edit bodies to use from all visible. I want to go to select, and here I
why do we have to take like a million things just to do like
no, maybe I'm doing it. I mean, there are thousands of ways to remove that screw. You could just remove the polygon and update it. This is all I used to do it, so I don't. The same with modeling. I did a quarter of the model, mirrored it, then but you could do it different way, maybe more simple. I don't know. It's just a habit that you just need to get rid of that. You could also remove the mesh as well, but it stays there in your monitor. Then you have to hide it. But yeah, let's continue. So I have it now. I can go back. I double click here, go back to the simulation, and you see the face gluing is not wrong because I actually don't need it. There is no washer face. There is no screw. Let's get rid of that. Force is okay, and constraint is okay. Now let's try this. I have to go to meshing, so I activate meshing. More. Where is it? Here. Bolt connection. So on the top, you have different options. You can do bolt with a nut. And let's see it first, then I show you. I'll put a bolt in tapped hole as well to see how it looks. And we're not going to use a spider at junction. That's for something else. You can simulate a rivet with that. But let's stay with bolts with a nut. That's what we have here. First one is the head, the second one is not. The head is asking for a whole edge, which let's assume this is the whole edge. Then after I apply, you see what happens. Then I explain this percent of whole. Let's go with 100% now, so everything is the way I select. The second one is not, and is this side. Again, let's stay with 100. Then I'm gonna change it back, but let's see how it looks like first with 100. What is that? How many? Why you have so many? Okay. Why you need to show the? Okay, decimal points. Maybe I have to change defaults. Yeah. I think it was a double variable, but the programmer didn't want to. Anyway. So here, the way it works is that now NX is just putting a 1D connection, which is a line, instead of the shank of the bolt. But it is just a line, but it has a cross-section properties that is implemented with a C-bar in NX, or C-rod. If you're sure it's circular, you can go with C-rod, which I will go with C-rod in this one. But technically, as you can see here, you can have any cross-section for the bolt actually. So I can select a C-beam, which is going to be a cross-section of a beam, a square shape. You can assign any cross-section to 1D connections without actually meshing it. So it's going to behave like a beam, for example, if I select that, but I don't need to mesh a beam. That saves a lot of computation time. So let's go with a C-rod, and that's the element properties. And I want it to be, I want to have RB, and the next thing is the actual head. How does it represent the head? Let me click apply just to, why do I have a different, oh, sorry, here I selected the wrong side for the nut. Let's go with circular edge here. Come on. On the this side, I think we missed. Yeah, there should be one. It was 53. I don't know why. Okay, now it's correct. Now you see how it actually represents a bolt. I will come back here and edit it again, but I think I made two. I have to get rid of the wrong one. Let's remove. Yeah. Okay. Now we are good. So a bolt is now represented like this. There is a spider element representing the head, and there is a 1D element representing the shaft. And the axial element, the spider element, is a rigid body element, so this one is rigidly connected here, but with RBE3, which is a more flexible rigid element, so it won't make this hole a rigid. Otherwise, you won't see any deformation on the side, which we don't care. We only care about the axial load on the shank of the bolt for now. But let's go back and let me remove this and make it again. Or maybe I think it's easier to just remove it and do a new one to see the different ways of doing it. So let's select again. This is the head. Come on. This is the knot. And now let's say in reality you have a washer face. A bolt is not going to sit right on this edge, right? It's going to sit on an area a little bit bigger than the hole, which is the washer head. You can specify that as a diameter here if you have it. I think for M10 is around 15. Or you can write a percentage. Like if I write 120 the way I had on both sides, you better go with a diameter, but I don't have it for M10. And if I click OK, now I think I need to, yeah. Please stop that. Now it's a bit difficult to see what's going on, and if you did it correctly without cross section and everything. So the way you make it visible, you go to this chord, First, you assign a material. I want the steel.
When you change 100 to what in this percent of whole?
120.
How can you delete it? Because it can't be deleted.
Yeah, I can't delete it either, but I just
Okay.
put it in new one.
Let me do it again. You just click on both, right click, you have delete.
Yeah, you don't have that.
Yeah.
Right click on 1D. Okay.
You don't have that option.
Is it activate simulation here in the top?
No,
Yeah.
No.
Click on activate machine.
I can't activate the machine.
You have no different plan.
Well,
Why is it so bad? It's
Ah.
insane.
I have changed this plate part.
I will do it again.
The bolt connection you wanted what? You select both of the edges.
Select this edge.
Yeah.
I have to. I did it wrong. Actually, you select. Let me deselect. So this is the plate. This is the head edge, and then you go for the knot and select this one.
Yeah.
You can go with a rod if you have the area of the nut or area of the shank, or you can go with a bar if you want to actually define it. I don't have the area, so I go with the bar. Let's see if it's easier. It gives me more options to define. And the rest of them, as I said, the spider element is the washer head.
You want C bar, right?
Yeah. We can change that later if we want. And what else here? Yeah, for now there is nothing else I want to change. So it should look like this. And then I go under 1D connection, double click on the bar. Now I want to define specifications for that central or axial element. Click here. You can select material here, which is a steel. Then you need to define the section. And click here, add a new section. Now you have options. I'll go back. Okay, let me go back. Are you here?
No.
Where are you? Okay, let's go back. Like double click on the bar collection.
Yeah.
Okay. Brings up this. Double click on the wrench, editing the bar property, right?
Yeah.
Okay, here you can assign material.
Oh, you have to
Why does it look like this?
green arrow to expand.
Yeah, if it looks different, just click on the arrow on any dialog box.
Green arrow. All right.
Yeah, this one. Yeah.
Here, it looks like this, right? Sorry. Now you're happy? Okay. Okay, you click on the. You don't even need that. No. This is only that's why you don't need those options. So select the material, and then here it allows you to define sections. And in this you need create new section.
Where did you do that again?
Okay. Here, this is small. Show section manager. Are we good? Then create section.
Yes.
Okay. The cross section of a screw is a rod, but you could define 2 bar, box, whatever. I go with a rod, and it is asking for radius, which is 5.
No, sorry.
Yeah. And click OK, close, and OK, and OK. Just click OK everywhere and close it. Now it's still not very good visible if we did it correctly, so you can actually right click on the bar collection, go to edit display, right, and it gives you this option of display section. You can select if you want NX to actually apply the cross section all over that element, and if you do this you actually see it as a solid like this, and then you just tell me where you're stuck. Maybe I can. Right click, edit display, display section. Change it to solid. What? On the collector.
What?
What? Okay. And yeah, then I can see if the screw is actually or the bolt is actually correct. This is just extruding only on the display, only on the view. Okay. On reality, it's just a 1D section with the properties of a shank or circular cross section. But NX can show you how it behaves actually. So I don't need to mesh it anymore because I'm representing the shank of the screw just by a 1D element with this kind of cross section. And let's go back and run the simulation and see if it works. I activate simulation. Let me check it again before I move the constraints. Okay, should be fine. Or we get an error and it's a new thing to learn about NX. For this one, it probably takes same amount of time. We only have one screw, and meshing it or representing it with 1D element doesn't change the time consumption that much. But if you have 100 screws or 50, 100 screws, it changes a lot if you represent it by 1D screw or by hundreds of elements. Okay, let's go to the result. Yours is probably different. So let's go back to simulation. Right click here on the solution. We have to ask for information of bolts. We did a bolt connection without asking for the report. And NX doesn't know. So click on edit. Go to the case control, output request. Click on the wrench. On the bolt result, you have to enable bolt result or request bolt result.
What was the preload option that says I do?
I'm going to apply preload later because we don't have it in a theory. Don't want to mix it with this. I want to compare it to this one.
It gives me an error because it says we need a preload to be applied.
When you click something's load. Okay, you should probably remove the load thing applied on your system somewhere. Yeah, do it again, constants. I don't know why it's removed. But okay, here you need to request the bolt result. So it appears on the result when you run the simulation. And if you do and you run the simulation, go back to the structural, you have one extra result here, which is axial stress elemental. And if you double click on it, it only brings out that the axial or 1D elements. I don't even need to probe it. On the left you see it's 1273, which is exactly, not exactly, but very similar to what we did with meshing. But with only one element, which is super fast comparing to meshing the whole thing. And at the same time you can see the stress on your part as well. So if you click on the element nodal, you see the stress on the part, and the washer face also represented here because we specified 120%. So it extends that spider element 20% more to represent the washer face. So you actually have a perfectly good result comparing to the theory, but without meshing the whole screw or the whole details of it.
How did you?
There was another type. There are more types, but another important type is that having a screw on one part but threaded on the other plate. How do you represent that? Which is that one as well is very simple. Let me remove that. I'll go back to meshing. I remove it because it's easier to see. Otherwise, it overlaps. So I go to the bolt connection and switch to bolting tapped hole. Same thing. You select the head, and then instead of not edge, you select tapped surface, which is that one. and it will ask you what is the bolt length. I say 20. Effective thread length is 10, because one plate is threaded and it's 10 millimeter. The other plate is not threaded and it's 10. So the total length.
Selected both of those first.
It threads everything. It threads all the way. Yeah, and it's not a good way to connect two plates like that. Yeah, one should be without. Yeah, one should be loose, while other one should. Yeah, and same thing. I can actually change the stuff here, but I don't. But I just want to show you how it looks. Now I don't know if it's good enough to see, but I can just remove the plates one by one to see what's going on. Now on the other side, you see we have a 3D spider that just grabs to everywhere. This means that the screw actually connects to everywhere on the threaded side, which is the way it actually works, right? When it threads, it connects everywhere. But on the plate side, I mean on the not threaded side, it looks like this. So this is a screw represented only by one needle. Gives the exact result if you mesh everything. And yeah.
Wouldn't the effective area of the bolt be smaller in the place with the threads?
Yeah, that's why there is a 4 section when you define the section. You can add, I don't remember, rear section or something like that. So it tapers in between. Or you can define different cross sections at different places. But the best way and safest way is to go all the way with one section, which is the core or minimum diameter. That's the safest option. And we're going to do it like that instead of representing it. Because if the shank is bigger and thread is smaller, it's going to fail around the thread, right? You just represent everything by minor diameter and you're going to see the failure. And yeah, so that's it for today. And next time we're going to add preload here.